This video is meant to be a review of the trigonometry that you've learned in grade 10 and grade 11. Not an entire comprehensive review, but a lot of the concepts that you will need moving forward to be successful in grade 12. So, when we talk about trig ratios, we either talk about primary or secondary ratios. When we talk about the three primary trig ratios, all they do is compare different side lengths within a triangle that has a right angle. Sine compares, hey, how big is my opposite side compared to my hypotenuse, which can often be shortened to O over A. Cosine compares two different sides. It says, hey, how big is my adjacent side to my hypotenuse, or adjacent over hypotenuse. And tangent compares how long is the opposite side compared to the adjacent side. And they are simply just ratios of values to compare the two side lengths when you're in a right angle triangle. The hypotenuse is always the largest side of a right angle triangle opposite the right angle. The opposite and adjacent sides really depend on what it is that which angle you're targeting to talk about. If I'm going to talk about this theta angle here, well, this is always my hypotenuse. Always, always, always. However, if I talk about this angle, then if I were to fire a bullet out of that angle, I would hit the opposite side. If I was to talk about this angle, then the opposite side would be over here. But the opposite side to my theta angle is here my 2.1 centimeters, which means that this is my adjacent side, and adjacent means right next door to, so this is the right next door side to my angle. So opposite, adjacent, and hypotenuse. So if we were to use the three primary trig ratios to solve for how big is theta, well, we know our opposite side, we know our adjacent side, and so opposite and adjacent, the trig ratio that compares those two side lengths is tangent. And so I can say, well, the tangent ratio for this mystery angle theta is going to come from a 2.1 centimeters compared to or divided by a 3.5 centimeters. And then inside your calculator, all stored up are all of the ratio values for the different angles in a right angle triangle. And the way we ask our calculator to find the mystery angle that goes along with a ratio is to use the tan inverse function. On a calculator, that's a second function of the tangent button for the tan inverse. And I wouldn't bother trying to find the number of 2.1 divided by 3.5. Calculators are fabulous to do the calculating, so let it do the work. Just plug in the 2.1 divided by the 3.5, and we find that theta is approximately equal to a 30.96 or a 31 degree angle size. And so using our primary trig ratios, we can find, we only need to be given three pieces of information about a triangle: the 90-degree angle, the 2.1, the 3.5. I've got three pieces of information, and so I can use my primary trig ratios because they were inside a right angle triangle. Now, this symbol here, this abbreviation, CSC, is calling for the cosecant, which is another ratio in a right angle triangle, but it's not a primary ratio, it's a secondary trig ratio. And they are just the reciprocal of the other trig ratios. Cosecant is the name for the reciprocal of sine, shortened up to CSC. So the cosecant ratio for a mystery angle wouldn't be comparing the opposite, hey, how big is my opposite compared to my hypotenuse? It compares how big is my hypotenuse to my opposite. Secant is the name given to the ratio that is the reciprocal of cosine. We shorten it up to SEC. And so secant isn't adjacent over hypotenuse, it's, hey, how big is my hypotenuse compared to my adjacent side length? And then finally, the reciprocal of tangent is cotangent. And so the cotangent ratio, COT, is the short form for that. And it's not comparing the opposite to the adjacent. It is comparing how big is my adjacent side length compared to my opposite side length. And so it's just the reciprocal of the three primary trig ratios. So if I'm given a question where I know the cosecant ratio, I know that the hypotenuse is 1.7 times bigger than my opposite, and I know that I have a mystery angle that has the hypotenuse and opposite being those compared values, then I can say, well, if I needed a denominator, it would be 1. And so my opposite side length, my hypotenuse, on top, my hypotenuse is on top, my opposite is on the bottom. And so if I were to just flip that over, and then instead have the opposite on top, opposite and hypotenuse, we are talking now about the sine ratio. And so if we are given one of the secondary ratios, we can simply make the reciprocal and call for the primary trig ratio. And the reason we need to do that is because no calculator I've ever seen has a cosecant button. They only ever have the sine, cosine, and tangent buttons. And so, I mean, if we had a cosecant button, we could just use it. We don't. So let's ask for the sine inverse of that 1 over 1.743. And again, I wouldn't try to find some number for that. I just let my calculator do the work. And when we let our calculator do the work, the sine inverse for a 1 divided by 1.743, we get that it is about a 35-degree angle. So approximately 35 degrees. If you have a 35-degree angle in a right-angled triangle, and you had a hypotenuse that was 1.7 times bigger than your opposite side, then that angle would be 35 degrees. Now, you simply need to remember your opposite over adjacent. Oh, my goodness. This should have been hypotenuse. Opposite over hypotenuse. Adjacent over hypotenuse, opposite over adjacent. The whole SOHCAHTOA is one way of remembering it. There's lots of different mnemonics that you can remember that with. Primary, secondary trig ratios used in right-angled triangles. Now, the joy of grade 11 was we started using angles that were bigger than what could be put into a right-angled triangle, into any triangle. And so we started needing a new way to talk about angles if we're going to pull them out of triangles. And so what we do is we draw angles in standard position. Now there's some rules about standard position. We have our 4-quadrant grid. We name the grids quadrant 1, quadrant 2, quadrant 3, quadrant 4, and that is the way that we cycle through these quadrants. We always, always, always have what's called an initial arm, always sitting along my x-axis, and that one never moves. What does move is a second arm that can swing around, joined at the origin here, to prescribe an angle that gets bigger and bigger and bigger. So let's say I have an angle that goes into my second quadrant here, and I would be using a second arm swinging around, and we call that the terminal arm. So my initial arm never moves. My terminal arm swings around. So it prescribes an angle that can get bigger and bigger and bigger as we go around the circle. So let's call my initial angle theta. When we have an angle that's bigger, this one could be put into a triangle, but it couldn't be put into a right-angled triangle, and so I can't find the sine, cosine, and tangent of an angle unless it's in a right-angled triangle. So what we need to do is talk about how I can manage to find all of the trig ratio numbers for this larger angle based on another angle that is very, very special. It's called our related angle or our reference angle. You'll hear it called two different words. This is very important. A related angle or a reference angle. And that one is key in finding, if you can find the numbers for this related angle, it's key in finding the sine, cosine, and tangent numbers for the big indicated angle. And so what we need to do is talk about how special these reference or related angles are. So associated with every angle drawn in standard position, there's another angle called the reference angle or related angle. Our textbook calls it related angle quite often. The reference angle is the acute, the tiny small angle. It's always less than 90. And it is always the acute angle formed between the terminal arm and the x axis, not the y. It's always the angle that goes from the terminal arm back to the x-axis, not back to the y-axis. So let's have some practice here, drawing some angles in standard position and finding their related angle. So I have to start with my initial arm on the x-axis. If I am going to show 140 degrees, that's certainly bigger than a 90, into my second quadrant here. So that might be a rough estimate of how big 140 degrees might look like. And then I want to talk about this angle here. This angle here is my related angle, or my reference angle. How big is that angle? Well, it's always the angle back to the x-axis. So it would be that half circle, or 180 degrees, except for that 140 degree part. And so it is 40 degrees. That reference angle to 140 degrees is my 40 degree angle. 240, well, I still have to start on the x-axis. I still need to swing around past the 90, past the 180, into my third quadrant this time. There is my indicated angle of 240 degrees. What is my reference angle? It is always the angle back to the x-axis, between my terminal arm and the x-axis. There is my related angle. How big is that related angle? Well, it's past the 180. It is 240 degrees, except for that first 180. That's how much my related angle is. So 240 degrees, take out that first half circle, and you will have a 60 degree related angle for an indicated angle that is 240 degrees big. What about some ones that aren't quite typical, landing in one of my first four quadrants? 360? Well, 360 goes all the way around. It is a full turn angle. So what is the angle between my initial arm starts out, the terminal arm swings to land in the very same spot. How far away is my terminal arm from the x-axis? It's 0 degrees. So the related angle to a full turn 360 degree angle is a 0 degree angle. 400 degrees? 400 degrees is bigger than a full circle. So to show a 400 degree angle, I would go around to the 360. Now I still need to go past my 360 to land the full 400 degrees. So there would be a 400 degree angle. Landing back in my first quadrant. How far back in my first quadrant? What's my related angle? Well, it's always the angle back to the x-axis. So my related angle is going to be that 400 degree angle minus that first full circle. And we will get another 40 degree reference angle or related angle to the indicated angle of 400 degrees. Now, in standard position, when you are asked to talk about a negative angle, the convention to show positive angles is to start and go around in a clockwise manner. A negative for an angle size just indicates the direction. It means you're not heading around in the normal direction of things, you are going backwards. So a negative 210 degree angle, I'd go negative 90, past the negative 180, into the third quadrant. And so there would be my negative 210 degree angle. Always label your indicated angle. And then where is my reference angle? Well, again, it's this angle here, back to my x-axis. My related angle or reference angle in that manner is going to be, now this is where we don't care the direction. We just want to know how big is it? Well, it would be that 210 degrees, except for that half circle. Direction is unimportant with a related angle. We just want to know how big is it? Well, it is 30 degrees. And so the reference angle, it's very, very important to be able to find the reference or related angle for a larger trig angle. Okay, keep going with terminology. Coterminal angles. When you are asked to talk about coterminal angles are any angles that share the same terminal arm. Now they will share the same initial arm as well because that never moves. However, the important part is that they share the same terminal arm. So if we were to draw a 120 degree angle, so there's my initial arm, would swing past the 90 into the second quadrant for a 120 degree indicated angle. So maybe about there. There's my terminal arm. I'm supposed to find the reference angle and two coterminal angles. So we already know The reference angle is this angle here, back to the x-axis. So my reference angle in that manner would be 180 degrees except for my 120, so that's a 60-degree reference angle. A coterminal angle. Well, my coterminal angle means that I need to land another angle on that very same terminal arm. So how do we do that? Well, I could talk about the negative angle. I could start here and go in the opposite direction and land on that very same terminal arm, which would mean I would have a negative angle. How far negative? Well, I would go the half circle, 180 degrees, and that 60. So that would be negative 240. That would be a coterminal angle. How would I get another coterminal angle? I'm trying to find another color here. Maybe green. Another coterminal angle, well, we could simply go around that circle a few extra times. I'll start little in the middle. If we went around a full 360 degrees and then landed on that coterminal arm, or so that terminal arm, we would have a coterminal angle. We would have the first 360 degrees and then another 120. And so 360 degrees and 120 would be 480 degrees as another coterminal angle. And so my coterminal angles, my related angle or my reference angle is 60 degrees. My two coterminal angles would be negative 240 and 480. Now, what we want to do is talk about why these are significant. If I took the sine of 120 degrees, and we just punch that into my calculator, so the sine of 120, comparing the opposite to the hypotenuse, so the opposite would be 87% the size of the hypotenuse. So we've got a 0.8660-ish. Let's try the sine for 60, that related angle. Well, the sine of 60. Look at that. The sine of 60 is also 0.8660. I get all the same ratio numbers. What about that coterminal angle? The sine of, let's try the 480. Sine of 480 is 0.8660. And finally, that last one, the sine of, and there's an infinite number of coterminal angles. We could go around that circle many, many times. The sine of negative 240, 0.8660. Look at that, 0.8660. So when we have a situation where we're looking at an indicated angle of 120, it will have the very same sine ratio, cosine ratio, and tangent ratio numbers than the reference angle or any other coterminal angle. Same holds true if we have a negative angle. A negative 100-degree angle would be just past the negative 90. So an angle in my 1, 2, 3, the third quadrant, so a negative 100 degrees. Again, what's my reference angle? It's the angle back to the x-axis, doesn't matter the direction, and so that's going to be an 80-degree reference angle. Another coterminal angle to that, well, we could talk about the positive coterminal angle there. The value of that, if we have 100 degrees out of 360, that's going to be 260. And we could go another full circle if we want to, but the idea here is that we want to talk about these very important trig ratios. So let's compare the tangent of my negative 100-degree angle, my 80-degree reference angle, my 260-degree coterminal angle, and we could do all kinds of other coterminal angles and get these very same results. What's going to happen here, tangent of negative 100, remember that number, we get a 5.67-ish, so approximately 5.67. Tangent of 80 degrees is again a 5.67. And the tangent of 260, 5.67. So what we have looked at here is the fact that coterminal angles will have the same ratio numbers. And I meant to change this before I copied it. Not and therefore, but because they. Coterminal angles have the same ratio numbers because they have the very same reference or related angle. The reference angle has the same ratio numbers as your indicated angle. Always, always, always. Sine, cosine, and tangent. And so therefore, your coterminal angles will all have the same reference angle, will all have the same numbers. Remember cast rule? Cast rule was good for not getting the numbers. The reference angle gets us the numbers, the ratio numbers for 120 degrees. We could use the 60-degree angle to get the ratio numbers for our 120-degree angle that can't go in a triangle. But cast rule reminds us of these negative positive ideas, because if I ask you the tangent of 100 degrees, we get a negative number with a 5.76. And so we need to have a code for remembering when our ratios are negative and when they are positive. You could have or would have been asked in grade 11, find the primary trig ratios for each of the following points on the terminal arm of an angle in standard position. So if I have an angle in standard position that goes through a point over 3 up 4, so let's pretend we go over 3 and we'll go up a value of 4, we'll land our point over 3 up 4. And so I want to talk about the angle that was made because we have a terminal arm through that point, so my initial arm over here, so that's my angle theta. Okay, well, when we're talking about angles, we need a triangle, so let's drop that triangle from my point as a right angle, and this side length will have been over 3, and this side length would have been up 4. So at this point in time, the only thing I don't know is the side length of my hypotenuse, but with Pythagorean theorem we can find that pretty quick. And they usually label this R, because what happens is if this terminal arm swung around with this point on it, it would prescribe a circle all the way around my origin here, and this distance would then represent the radius of that circle. And so r squared, the hypotenuse of this triangle, would be equal to 3 squared plus 4 squared. So r squared is equal to 9 plus 16, or r squared is equal to 25. Square root both sides, and we know that r is 5, a classic Pythagorean triangle, a 3, 4, 5 triangle. And so once I have all of my side lengths, I can say, well, the sine of that mystery angle theta would be made of my opposite side divided by my hypotenuse. And so we would have 4 over 5. The cosine value for that mystery angle would be made of the adjacent over the hypotenuse. So a 3 over 5. And you ask me the cosine ratio the tangent ratio for this mystery angle, it would be opposite over adjacent. So a 4 over 3. But what is important to realize is that sine is positive, cos is positive, tangent is positive. All ratios for any angle that lives in the first quadrant, they will all be positive. All of those numbers that you will calculate for angles in your first quadrant. All right, well, let's swing an angle over into the second quadrant, perhaps with a coordinate like negative 12. We would go perhaps back 12 and then up 5, land our point of negative 12 and 5, and we want to have our initial arm over here and our terminal arm running through it. Now that will prescribe this angle here, this big theta angle, an obtuse angle that can't live in a right angle triangle. However, what we want to do is we'll take a peek at this related angle here. My related angle is always the angle back to the x-axis. And if you remember, the related angle always has the very same ratio numbers. So whether they're rotten rounded decimals or whether they're exact values, the related angle will always have the same numbers as my reference angle. So the right angle triangle I can make here encompasses the related angle in here. But I know that the sine of my indicated angle will be a number, and it will be the very same number as the sine of the reference angle. So if I can find the sine of the reference angle, then it is the same as the sine of that indicated angle. So I know I would have gone back 12 for this side length and up 5 for this side length. My r squared here is equal to my 5 squared plus a negative 12 squared. So r squared is 25 plus 144. So my r squared is 169, and the square root of both sides means that the r value is 13, another classic Pythagorean triangle, 5, 12, 13. So the sine ratio for this large angle is the very same as this reference angle, so that will be opposite over hypotenuse. So a 5 over 13. Likewise, the cosine ratio for my big indicated angle has the very same numbers as the cosine ratio for my reference angle. This time it is adjacent over hypotenuse. Sorry, adjacent, negative 12. That's my opposite side. So my adjacent, but this time it's a negative value. And so cosine's negative in this quadrant because it uses a negative measurement of negative 12 for its adjacent side length. And tangent for this angle, large prescribed angle, is going to be the very same number as my tangent for my reference angle, but we have an opposite over adjacent. We have a 5 over negative 12, but we never leave a negative in the bottom, so let's just tuck it out front or up top to have good math form. So for all angles that land in my second quadrant, they're going to be using a negative adjacent side length. And so cosine and tangent both use that adjacent side length, so both of them will always be negative, and only sine is positive for any ratios for any angle that land in the second quadrant. If we land a third quadrant angle, perhaps we go back 1 and down 1, an equal value here. And so I start with my initial arm cemented to that positive x-axis. I swing an angle around so that my terminal arm lands here. So there's the angle that is prescribed by the angle that, or the terminal arm that goes through that point, -1 and -1. So that angle, I am going to use the reference angle to find the sine, cosine, cosecant, secant, cotangent, all the same, all those values for this large indicated angle can be found using my reference angle. So let's make my triangle back to the x-axis here with my right angle there. And I do know that we went -1 and -1 down. And so -1, -1, all we need is a radius value. So my r squared is equal to -1 squared plus a -1 squared. So I get 1 plus 1 is 2 for my r squared. So r is the square root of 2. And we don't want any rounded decimals, so we'll leave it as a square root of 2. And so the sine of my related angle or indicated angle is the very same as my related angle. So I'm just going to skip that extra step of writing it. The sine for my theta is the same as the sine for my related angle, which is opposite -1 over hypotenuse of the square root of 2. The cosine of that indicated angle is the same as the cosine of my related angle, which will be adjacent over hypotenuse. And then tangent for my related angle is, or for my indicated angle, is the very same as the tangent over my related angle. Opposite over adjacent, well, that means I've got a negative over a negative, which will just result in a +1. And so both the opposite and the adjacent side lengths are negative for angles that are reflex angles landing in the third quadrant. So all of the sine, cosine, tangent, cosecant, secant, or cotangent ratios, of all of those, it's only the tangent that uses both the opposite and adjacent, so then becomes positive. So only in this quadrant, tangent is positive for ratios for angles this size that they land in the third quadrant. Finally, the 15 over 15 and down 8. So over 15 and down 8, perhaps here. And we start on the initial arm. We swing a terminal arm all the way around that origin to land in the fourth quadrant. So the angle we are really talking about is this angle here, a very large reflex angle, smaller than the full circle, but landing in my fourth quadrant. The related angle for that is right here. So if this is my indicated angle, my related angle is the angle back to the x-axis, always, always, always. And so that is the angle that's going to live in my right angle triangle. I knew that I went, let's mix these up. I was going to say negative. I went over 15 and down the 8 so that we have a negative value for the opposite. And again, r squared is equal to my 15 squared plus my negative 8 squared. So r squared is equal to a 225 plus my 64. R squared is equal to a 289. And the square root of 289 is a 17. So I get a nice even value for my 17 hypotenuse. And so the sine of my indicated angle is the very same value as the sine of my reference angle, which will be opposite negative 8 over the hypotenuse of 17. The cosine of my indicated angle is the very same value as the cosine of my reference angle, which will be the adjacent side length 15 over 17. So we get our two positive values there, creating a positive tangent or cosine ratio. Tangent ratio for that theta value is the very same as the tangent for the reference angle, so I get opposite over adjacent. And so I get a negative tangent ratio. And so in this quadrant, in my fourth quadrant, the only ratio that uses the positive values is cosine. So only cosine is positive. And this is the origins positive of our cast rule, C, A, S, and T. Now I haven't put them in a four quadrant orientation, so let's do that down here. When we look at a four quadrant orientation, angles that land in my first quadrant angles, these angles all are positive. So let's put the A for all. All ratios are positive. And then in the second quadrant, only sine. And it's only sine. The other two are negative. Only sine is positive. And so it's important to remember that cast rule reminds you of which ratios are positive. Then if we swing an angle around so its size lands it anywhere in the third quadrant, of all the trig ratios, only tangent is positive. Again, cast rule reminding you of what is positive. And then if an angle is big enough to land in that fourth quadrant, then only cosine. C-A-S-T is positive. All right. You likely have seen this abbreviation for sine, cosine, and tangent, where we've got x over r, y over r, x over r, and y over x. Where that generates from is to just talk in general. We cemented rock solid numbers there with the cast rule, but if I have any angle size with an initial and a terminal arm, if I was to talk about a point and drop a right angle, then I would have gone over x amount of units and up the y amount of units, and then r would have been my hypotenuse measurement. Now, the r squared is equal to my x squared plus my y squared. That's just Pythagorean theorem. The hypotenuse is equal to the addition of the other two squares. And so r on its own is the square root of x squared plus y squared. And if we talk about the angle that is prescribed with any of the angles that could go around a circle, then the sine would be my y coordinate over the size of the hypotenuse, the radius of the circle if it went around the circle. Cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. So you can, if you know the coordinates, the xy coordinates, you can know the sine, cosine, and tangent for any of those values. So, moving on as to why this is useful. Well, when we use trigonometry for angles that are larger than 90 degrees, the fact that you have a reference angle will give you the right ratio numbers, and then reminding yourself of cast rule will give you the right positive or negative value for those ratio numbers. So to find trig ratios for angles larger than 90, the reference angle will give you the correct ratio numbers, and cast rule will tell you whether the ratio is positive or negative. So find the exact value for the cosine of 135 degrees. Now, to find the exact value of the cosine of 135 degrees, we have to remind ourselves of two very special triangles. One of them we would have learned, or both of them we would have learned in grade 11. If you have an equilateral triangle, then you have a 90-degree angle in here, then this has to be a 45, and this one has to be a 45. We have a 1, 1, and then a root 2 as the hypotenuse measure for any angle, for any triangle that has two 1s, then the hypotenuse will be a value of the square root of 2. Hopefully that sounds familiar. The other very important triangle is if I have another of my set of important trig angles, if I have my 30-degree angle in a triangle with a 60-degree angle and a 90-degree angle, and we call this side length 1, then this one is a 2, and this one is a root 3. Those are our special triangles. And so if we have an angle that has a related or a reference angle that can be found in one of these special triangles, then we can find the exact value for the larger angle size. So let's find the cosine ratio, or the cosine value, the exact value for 135 degrees. First thing we need to do is draw it in standard position. Step 1, draw it in standard position and find the reference angle. So we have our initial arm on the x-axis, and we'll swing 135 degrees past the 90 into my second quadrant. So there it is. Always label it. There's my 135-degree angle. Now I need to find my reference angle. So my reference or related angle here is going to be this angle here. A reference or related angle is going to be the half circle except for the 135 degrees that we already had. So 180 degrees except for the 135-degree part of it means that I have 45 degrees left over. Oh, imagine that. We've got a special triangle with a 45-degree angle in it. Now here is where we write an equivalent expression. I am going to find you the cosine value for 135 degrees, and I'm going to get the right numbers from the cosine of the related angle. So the proper ratio numbers are going to come from the related angles. So let's drop the right angle. There's my 45 degrees. And so I have a 1, 1, root 2 triangle, and I want cosine. And so I'm going to get the right numbers from that. But cast rule reminds me whether the ratio numbers are positive or negative. And so cast rule, C-A-S-T, I am landing an angle into the quadrant for which sine is positive. And if only sine is positive, that means that cosine is negative. And so get the right numbers from the 45-degree angle, but cast rule reminds you that this ratio is going to be a negative ratio for the cosine of 135 degrees. It will be a negative value, and the cosine for 45 will be adjacent over hypotenuse. And so the exact value for the cosine of 135 degrees will be negative 1 over root 2. Let's try that again, but this time with a secondary trig ratio. Now I know that the cotangent of 330 degrees is the reciprocal value, or 1 over the tangent value of 330 degrees. So I'm simply going to find the tangent ratio of 330 degrees. And then in the end, when I'm done, I'm going to flip it upside down so that it is the cotangent ratio. So first thing I do is draw my angle in standard position and find the reference angle. So if I start here on the the initial arm, past the 180 mark, past the 270 mark, into my fourth quadrant. So there it is. There's my terminal arm. There is my 330 degree angle. Now I'm not going to work with that angle. I'm going to find the tangent of 330 from the tangent of its reference angle. So I need the reference angle in here. And if I've gone almost all the way around the circle, then the full circle is 360. I've already gone 330. So I am looking at a related angle of 30 degrees. So I'm going to get the right ratio numbers from that 30 degree angle. So let's drop my triangle back to the x-axis, always, always, always back to the x-axis. And so in my 30 degree, I have my 30, 60, 90 triangle. That's one of our special triangles. And I always remember that my 30 degree angle is my smallest angle of my triangle, and it will be across from my smallest side length. The square root of 3 is a 1.7-ish. And so it's a medium-sized side length between 1.7, and 2. So that goes with the medium-sized 60 degree angle. And then my largest 90 degree angle goes across from my largest side length of 2. And so if I've got that triangle flipped around a little bit with the orientation here, and this is my 30 degree angle, it's still my smallest angle in that triangle. And so my smallest side length will be across from my smallest angle. My largest 90 degree angle, we're in that largest 2, and then the square root of 3, which is a 1.7-ish, will be across from that 60. How does that help me? Well, that's going to help me get the tangent ratio for my 330 from the tangent of my 30 degrees, opposite over adjacent. But I need to know whether it's positive or negative. And so cast rule reminds me that in this quadrant, only cosine's positive. So again, tangent has to be negative. So I'm going to find you, and again, this equivalent statement is very, very important. And in fact, it'll become more important in our next unit. So get used to writing that. The tangent of 330 degrees is equal to a negative value of the tangent of my reference angle 30. So negative from cast rule, and tangent of 30 will be opposite over adjacent. So a 1 over root 3. But remember, now we're not done. We didn't want the tangent of 330. We wanted the cotangent of 330. So therefore, the cotangent of 330, tangent compares opposite to adjacent. I want the adjacent over the opposite. So it will be a negative root 3 over 1, but we wouldn't write that. So find the primary trig ratio and then just flip it upside down to get that secondary trig ratio. Now, this final example. The final thing that you need to remember from grade 11 is pretty much doing cast rule backwards. So, a question like this. Here, in my first question, I knew the angle, I didn't know the ratio. This one, I have the opposite set of conditions. I don't know the angle, but I do know the ratio. And so, I'm given tangent of some mystery angle with a ratio of 1 over root 3. And I am asked to find the cosine and cosecant of this mystery angle. And then, once I'm done that, find what the mystery angle is. So, my tangent value of some mystery angle is 1 over root 3. What do I know about that? Well, I know that tangent compares the opposite side length to the adjacent side length. And so, I also know that these numbers look very familiar from a special triangle. A 1 and a root 3 live in a special triangle. So I'm looking for the angle, some mystery angle that is opposite the 1. It's here. Well, we already talked about the fact that in my 1, 2, root 3 triangle, opposite the smallest side length is the smallest angle. So it's a 30 degree angle. Now this is the reference angle that I'm finding. And so my theta reference angle is 30 degrees. And that will help. I used the numbers to find my reference angle. Before we used the reference angle to find the numbers. Here I had my numbers, so I found my reference angle. Now, how is that important? Well, I then ask myself, where do I plunk that reference angle? In which quadrant? So where is tangent positive? We were originally given a positive ratio, so cast rule will remind me that all of them are positive in the first quadrant, only tangent is positive in the third quadrant, and so I have two answers out of this. So let's draw two possible grids. I could land some mystery angle and just represent, we don't know how big it is, but just represent some angle landing in the first quadrant. And so if theta is landing in the first quadrant, I'm going to be using my reference angle, my theta reference angle in that first quadrant, that 30-degree angle. And so what is my theta angle? Well, it's the same as the reference angle, the angle back to the x-axis. And so the tangent of that angle, if my reference angle is 30 degrees, then so is my related angle. So my indicated angle is also 30 degrees in that quadrant. And so the tangent of 30 degrees is equal to a positive 1 over root 3, opposite over adjacent in that orientation. But we also know that tangent is positive in this third quadrant. And so if I start an angle and land it somewhere in my third quadrant, there it is. There's my indicated angle. But remember, I'm going to use my reference angle as my angle size to relate to my indicated angle. That reference angle is 30 degrees. So how big is theta? Well, theta is that half circle plus another 30 degrees. So 180 degrees plus the 30 means that the other angle that makes this true, the tangent of 210 degrees, is also positive 1 over root 3, opposite over adjacent, for an angle that lands in the third quadrant. And so if we're asked to find the angle, I have actually done this part of it, find theta. Well, theta could be 30 degrees as well as 210, because we were told that theta lives anywhere in the first full circle worth of degrees. Now what I haven't done is I haven't answered this part of it. Find the cosine of theta and the cosecant of theta. Well, if we know that the tangent is opposite over adjacent, then I can simply find the cosine of theta as the adjacent over the hypotenuse. So the cosine is the root 3 over 2, so adjacent over hypotenuse. And then cosecant is the reciprocal of sine, so it's hypotenuse over opposite. So a 2 over 1, which would just be a 2. And so if you're asked for, this would be two separate questions. Given that tangent is this, find me the cosine and cosecant. We could just get that from my, find the reference angle and then plunk it in this quadrant, or in this special triangle, and then find cosine as the adjacent over hypotenuse. Cosecant would be hypotenuse over adjacent, and we could find it directly from there. If we want to find theta, there's two answers for that, because tangent is positive in two separate quadrants. Finally, our last skill that I'd like to highlight from grade 11, same process, but this time there is no special triangle that has a 3 and a 5 in it. So how do we handle this? Similar manner, we want to find theta. Sine is negative, C-A-S-T. Sine is positive in these two, first and second quadrant, so I'm talking about an angle that could live in the third quadrant or the fourth quadrant, because those are the quadrants where sine would be negative. So the first thing I need to do is find my reference angle. I don't have a nice set of, a nice special triangle with a 3 and a 5 in it, and so if I'm talking about the 3 and the 5, I'm still talking about my opposite and my hypotenuse side, and so we don't have a special triangle, and so all we do is we go to our calculator, and we use our calculator to spit out the reference angle that we're going to use to put into the two different quadrants for which sine is negative. But I want to talk to you about this negative. I want to find the sine inverse of the ratio value. But if I ask my calculator the sine inverse of a negative number, so let's do sine inverse of a negative 3 divided by 5, my calculator tells me it's a negative 37-degree angle. Well, that's because your calculator is trying to find the closest angle to 0, which would mean it would land in this quadrant as a negative 37-degree angle, because sine is negative in this quadrant. And so when you're asking for the reference angle, don't use the negative, because negative is just directions on which quadrant. The acute reference angle, if it lived on its own, acute angles will only ever live in the first quadrant. So if you just want the acute angle size, don't put in the negative, just use the absolute value of the ratio, just use the 3 over 5. Because then if you ask your calculator, hey calculator, what angle would have an opposite side 3 compared to the side length of 5, then you get 36.86 positively because it's landing it in that first quadrant. So my theta reference angle, sorry, I should have put reference angle. Finding the reference angle means that I'm going to approximately use a 37-degree angle. Now, where is sine negative? Sine is negative in 2 quadrants, C-A-S-T. All are positive, sine is positive, and so you need to land an angle in the 3rd quadrant with your reference angle there. And when we land it there, it's a 37-degree angle. A 37-degree angle, I can hardly see that, in this quadrant. You want to know how big is your entire indicated angle? Well, it is the half circle plus 37 degrees. So 180 plus your 37, we're talking about a 217-degree angle. Now let's just double check that. 3 divided by 5 is a 0.6, and so we're talking negative 0.6 is what we want. The sine of 217 degrees, look at that, a negative 0.6. Now why didn't we get exactly 0.6? Because we didn't use exactly 3 over 5. We rounded here. And so the sine of 217 degrees is approximately pretty much equal to that negative 3 over 5. Finally, C-A-S-T. Sine is negative in this quadrant, but sine is also negative in my 4th quadrant. So the big, large angle I'm looking for is a 4th quadrant angle. I'm still going to use my reference angle, the angle back to the x-axis, the 37 degrees. So in this case, it's the full circle except for that 37 degrees. So 360 degrees minus that 37 degrees. And we are talking about a 323-degree angle. So the sine of 323-degree angle is approximately equal, let's check it, sine of 323, yep, it's a negative 0.6, which is the negative 3 over 5, approximately equal to that negative 3 over 5.